Mic check. Okay. Hello, everybody. Oh, great. Hello, little peeper. Good evening, everybody. I hope you're all doing well. Thanks for being here, as always. So, let me fix my display. Hello, Damien. Hi, baby doll. Who else is out there? Good evening, Tyler. You know, there's a Twitch achievement, but I'm never going to get it. But if I could get 35 different people in chat in one broadcast, I'd get an achievement. But I think mostly the achievements I'm going to get, I got, which are all the easy ones. Anyway, good evening. I have a fair amount of things to do, as always. Your class is one of the more intense ones that we do in computer science at Butte College. Bringing together a lot of your prior experience, plus learning new difficult things sometimes. So I'm very happy that you're all sticking with it, and we're going to make it to the end, and we're going to be successful at it. So if you've come this far, then you've got this. You're going to do good. So I made some notes for myself, which you can see on the side of the screen, about the things that I wanted to cover. And just to kind of point out for you, and this is also for people watching the video later, is kind of 3 sections here. So I'm going to have to switch gears between the 3 sections of tonight's meeting. So the first one is that the poll is closed, and overwhelmingly people voted to not do another team project. So I canceled it. I removed it from the schedule. I removed it from the syllabus. It's all gone, and I apologize to those of you who would have liked to do another one. I don't really have a good place to fit it into the grading scheme, but if anyone's interested in having at least the code base to play around with, I'm more than happy to share that with you. So you can just let me know either in chat, or you can let me know by a Canvas inbox message if anyone at all is interested in seeing the code base, at least for the second team project. I can release that, and you can at least have it to look at if you're interested. You've got plenty of work to do, so it's not like your workload, you're probably relieved about managing your workload. And I posted an announcement to that effect as well, that I scratched. But I used the term scratch because it sounded cool, but what I mean is Team Project 2 is no more. So long live Team Project 2, but it's been canceled. And then I wanted to show off a couple of examples of Team Project 1. So one thing that I was very pleased about is that every team submitted something that worked. So that was great. And most of the points that were given up were just here and there on little things, not doing the documentation, or maybe just lacking a couple of corners that could have been polished off a little. So anyway, good on all of you for doing so well on the first team project. And I'm going to show off a couple. One of them I'm going to show, and just because they did some cool stuff with it. So let me start with that and just show you how this one looks when it runs. It's pretty cool. So, wow, that's pretty dang awesome. How do you even do that? I'll show you the code, and then you can ask on Piazza if you're curious about how this was done. There's actually a Piazza discussion probably a month ago or longer that sort of led to this really, really spectacular result. So need to run it really, although I will run it a couple times. I just wanted to show you, wow, that's a really cool thing. It shows the extra work that went in it to pull that off. So let me go ahead and just run it a little bit. So pretty cool thing. And then there's the exit screen. So that's pretty spectacular. I think that's probably in the user interface code. So I'll just show you kind of what it looks like. So what they did is they figured out how to use, these are called escape sequences. They're codes that change colors and put different symbols on the screen and stuff. So dang, that's really cool. And then another one, I wanted to show you here the main thing. I already have the code pulled up because this team actually went in and took the time to figure out how my CN Reader library works. So they were able to actually go into my CN Reader library and customize the messages that came out on user input errors. So that's pretty awesome. They also used escape sequences, so that's pretty cool. I'll run this one. And then I'll do something naughty just to show you what they did. So I'm going to put in an invalid entry. So let's put one, let's put 999. So anyway, they managed to customize the outputs by using my CN Reader library's functionality. So I thought, wow, that's really cool. So only a couple of examples. Everybody who participated in one that worked more or less in the end. These two I thought just had a couple of features. One was the really splashy user interface, and this one was having taken the time to read the CN Reader code and figure out how to use it. They used it, and it was recommended, although not required that you use it. So it's a library that I have written, and then a couple of students over the years have found bugs, and they got contributor credit for it. Anyway, if you open this file up and you read down through it, it tells you how to use it. So there's examples of usage in here. So if you haven't used it, most of you did, I think, but if you haven't used it, there's a whole bunch of examples in here. There's examples that show you how to change the messages. So that's what that one team did, is they figured out how to do that and made it work for themselves. So pretty cool. Okay, so that's part one. Part two, talking about individual project two. So let me bring this, so I'm on the home page on Canvas. So individual project two, which I'm going to open in a separate tab. I actually have my notes up, so I can also sort of write some notes to sort of help you think this through. Okay, so this seems pretty scary, and if you go to the repository, all you're going to see is a comma-separated values file. So CSV is a standard format. It's basically a database in a file where the fields of each entry are separated by commas, comma-separated values. So that's the only thing that you're given for the second individual project. In GitHub, which is where I host your code base, it does this fancy little formatting thing. It actually even recognizes the comment line and makes little table headers out of it. But basically what this file is, if you look at raw, so it's tons and tons and tons of entries about countries around the world and some basic metrics of those countries. The first line is a comment, has a pound sign on it. So that's what the file looks like raw. It's a series of fields. Each piece of data is separated by a comma. So let me start making a few notes here. So individual project 2. The things that you have to be able to do. You have to be able to open and read the contents of a file. You've done this before. I think it was in Lab 6, where you did this very thing. So that's, to me, the first problem to solve is, can I get this file opened and can I read all the lines that are in it? Included in that are ignoring the lines that have the hash symbol on them. We've talked about that in class. Ignoring the lines where the 0 character or the first character is a pound sign. So we've done that. Let's see what else. We need to parse the lines. We've done that as well, where we read a file in and we parsed the lines, and by that I mean we took each line and we pulled the pieces apart and converted them into the proper data formats. So if you look at this file, if we look at the Afghanistan line as an example, let me zoom. This line right here. So you're going to have to pull this line apart and get 1, 2, 3, 4, 5, 6, 7, 8 fields out of it. The separator is a comma, and you've done separator characters, although maybe not a comma before. So you have a string field, an integer field, an integer field, and integer field, probably, a float field, an integer field, an integer field, and a float field. Now, one thing to be careful about, integer, integer, float. One thing to be careful about is assuming that something is an integer field when it might be a float field. So we're going to be careful with that. But anyway, part 1 is, can you open this file? Can you read in the lines of the file? And then can you parse the lines in the file? And we've done that. We did I think we did all of those things on Lab 6. So Lab 6 gives you the ability to read in this file and parse it. You're going to have to parse strings. Don't really have to be parsed. Integers do, and floats do. Let's go back the screen and just scan down here and look. We can kind of tell from this table view what are integers and what are floats. So there's a country field, a population field is an integer, the area seems to be all integers. The population density field has floats in it, so that should be a float. Net migration is floats. GDP appears to be integers. Literacy is floats. See, there's floats in there. And birth rate is floats. So as you're parsing the lines, you need to be aware of what the fields are. So the fields are a string, an integer, a float, a float, a float. This is the name. This integer is the population. This integer is the area. The first float that you encounter is the pop density. The second float you encounter is net migration. Oops. The third float that you encounter, nope, that's an integer. That's GDP. Then you have another float field. And the way I'm doing this is I'm scanning down the columns. So when I look down GDP, I don't see any floats. So it's safe for that to be an integer. Net migration, though, I see floats. So that needs to be a float. Population density, I see floats. Yeah, so there's a question, do you want us to use string to double? Yes. So you're going to have to use string to integer and string to double. Let's go look those up before we quit talking about this. So yes, you're going to use the string to conversions, and let's go look at C++ about those. Another question is, do we paste it as a .txt or CSV? It doesn't really matter. I would use .csv because that sort of would be universally recognized by programmer types as a comma-separated values file, but your code's not going to care. So when you paste it into your REPL, You can use .txt or you can use .csv, although most of us would use .csv. Just to be clear, that's the nature of the data inside. Okay, so good questions. Let's see, what was, literacy. And finally, birth rate, which is also float. Okay, so let's look at converters then. So one of them is STOD. So let's go look that up. And actually, I already pulled up c++.com for this kind of stuff. So let's go look up STOD. And remember, you gotta usually scroll down past the junk. It thinks I'm talking about, you know, a health issue. So here's STOD. And it will take, it should have a simple version of it. Yeah, you don't have to worry about that. So if you give it a string, it will return a double/float. So you need STOD. You also need, not STOF. You could use STOF. And then you also need STOI, string to integer. For the parsing work. So excellent questions about the converters. So when you're doing the parsing, you're going to need help because you're going to be getting everything as strings, and you're going to need to convert those strings into the proper data types. The reason why you have to do that, by the way, is because you have to put the data in order, and it's not going to be in the proper order unless it's in numerical form. So if you leave everything as strings, it's going to try to alphabetize stuff, and that's not what you want. Okay, so that seems like a lot, but you did that in Lab 6. You need to then so you have to take the parsed data and place it into a model, which I think we also did in Lab 6. Someone can correct me if that's wrong. Actually, I can just look at our schedule and tell what we did on Lab. File input, strings vector. Yeah, that's also Lab 6. So you're going to need to model the data. I would use a struct, but you can use a class, either way. So it's a struct or class that will be used to hold all those fields in one place. So that's another thing that you did in Lab 6. You parsed the data, you created an instance of a struct, and then you loaded up that instance with the data. So you're going to want to do that on the second individual project. Create a struct or a class to model this data that you have parsed from the file. You did that in Lab 6. Next, you're going to now I have to go smaller again. Store the instances of the model in a, I would recommend a vector. That's the easiest way to do this at this stage. Store the instances of the model in a vector. We started using vectors in Lab 7, and I think we also used them in Lab 8. Am I right? Yes. So open the file, parse the lines. You're going to have to convert some of the data fields to the proper types, and then you're going to use a struct to place all of the related fields together in a single instance. Once you've done that, then you're going to take that instance and you're going to store it in a vector. So what you're going to end up with at the end of parsing the file is you're going to have a huge vector with a whole bunch of country structs in it. Each instance is going to have all of the data for one country. So that's sort of the all of the getting the data into the computer so that it can then be used. So the next step after that is so you've done this as well. In Lab 8, so I'm pretty sure it's Lab 8, you're going to need a bunch of compare by functions because the whole purpose of your program is to sort the countries by their population or by their birth rate or by their net migration rate or whatever it is. You're going to get to pick, but the point of your program is to let your user view like the top 10 most populous countries or the 10 countries with, or 5 countries with the lowest birth rates, those kinds of things. So you're going to need a whole bunch of, not a whole bunch, but you're going to need several compare by functions. You're going to use standard sort with your compare by functions. That's also Lab 8. Why does this thing keep moving around on me? So you're going to be sorting and resorting and resorting the vector whenever the user says, hey, I want to see the least populous countries. If that's an option you offer them, then you're going to have to resort and then display. Okay, and then I want to show you one other trick. Actually, one other trick and then one algorithm. So standard reverse can help. So let me show you standard reverse. So reverse takes a collection like a vector and it flips it over. So if you look at the example code down here, notice that the example is actually, they start by creating a vector in order and then they use reverse to reverse it. So what this would allow you to do is use one compare by function for population, let's say. But if they want to see the least populous countries, then you sort by population and then you reverse the vector and then you print those out. So that can be a huge help. Okay, so hopefully those notes make sense. I'll give you one more hint about an algorithm, but that's the things that you're doing. That's labs 6, 7, and 8. That's all it is a variation on those 3 labs where it brings all those pieces together. So what I didn't put in here between the model and the instances is that you don't have to, but you might create a CRUD function class for your countries vector. So if you did that, then you could model your code on what we did in Lab 8. But it's a choice you can make is to create a class with the CRUD functions that allow you to do stuff with your vector. And we did an example of that in Lab 8. I don't need to save that. So sorry that these notes are, can I stretch them out? I can stretch them out a little bit. Let's see if I stretch them out, if it messes this up a whole lot. And now I'm unhappy with it. I didn't make it any better, I probably made it worse. I'll go back and review it real quick. Okay, so that's all the basic approach, and then I'm going to put down here at the bottom one last bit of note. And the last bit of note is, let me push this way. So this is just sort of a thing to think about. So let me just show you the sequence. You don't need to know that, no assumption. So what's going to happen is they're going to say, I want to see the 10 most, or I want to see countries by population. So your program after that selection, oh, I want to view population, the most populous countries, your program is going to do something like this. Countries. So you're going to ask them like, okay, do you want to see how many of the top of the most populous countries do you want to see? So you're going to read in how many countries they want to read. And then you're going to do this. So for, or you can do this. So let's say that their choice was, I want to see the 15 most populous countries, or the 3 most populous countries, or whatever it is. That's what this sequence is about. So if you read the specification for the project, your user has to be able to choose what to view. Like, I want to see the most populous countries, and then your program also has to ask them how many of the most populous countries, the 3 most populous, the 5 most populous. So you can just ask them, like, how many? And they can type in 7 or 2 or 4, or it doesn't really matter. You write a for loop to only go as deep into the vector as you have to, and then you do, assuming you have a countries vector, why does that thing keep being squirrely like that? So that's the way that that is a way that you can control how many countries they see. You don't want to show them all the countries. You want to ask them, okay, you asked for the most population, how much? Okay, you want to see 5 of them, so you just loop 5 times and you show the first 5. If you have done a reverse in here, then you show the last 5, which would be the least populous. So hopefully that makes some kind of sense. And then I'm going to go back, I'm going to review this, and then I'll go back and I'll look at the second project, and then we'll move on to part 3. So let's go review these notes. So what to do on individual project 2. The labs that are relevant are labs 6, 7, and 8. They do everything that you need to do this lab, 6, 7, and 8. Everything that you need to know is in those 3 labs. So you need to be able to open the file that comes with the project. You need to be able to ignore the comment lines. There's one, but you need to ignore it. And then you're going to parse the remaining lines. And we just went through and actually identified what the fields look like coming out of the file. The separator character, I can add that. The separator character is a comma separated values file. And then we also pointed out that these converters can help you get from the string data you're getting from the file into the program where you want to model it. Okay, so you've parsed the file, you've converted all of the fields to the appropriate data types. Now you're going to, at least I recommend that you do, you use a struct or a class to model the data, which is to collect all of these fields in one place. We also did that in Lab 6. And then I recommend, because you've done it before in Lab 8, create a class that has the CRUD functions in it that manage a vector of your structs. We did that in Lab 8. So that as you're parsing the file, you're creating the instances of the struct, and then you add them to your vector. Okay, so that's the whole what do you do with the data part. The second part is how do I show the data. So you're going to need a series of compare by functions. If you're using a vector, which is what I recommend, then you're going to need a series of compare by functions just like we did in Lab 8. I'm reminding you that the standard sort function is the trick in combination with compare by functions to get your data sorted by population or by net migration or whatever it is that your user has requested. The standard reverse function can help you go from the 10 most populous to, if you reverse it, the 10 least populous countries. And then the last bit of note is, so, okay, what if they say what if I allow them to pick how many countries to view, which you're supposed to do? Well, this is how that might go. You're going to ask them, okay, you chose population, how many countries? They type in a choice, and then you use that choice to control a loop where you only access the number of countries up to the number of countries they wanted to see. So that's the whole individual project to sequence in my mind. Hopefully that helps. I'm going to go back to the instructions here. So you do have a little bit of user input because you're going to have a menu. Your menu is going to say, please pick how you want to view countries. And you're going to offer them some choices. Totally up to you. How many do we have? A minimum of 5. So these are all of your choices, and you have to pick and do a minimum of 5 of these. So you're going to have a menu that has 5 of these that you picked. So if your user, like if option 1 in your menu is most populous, your user is going to type option 1. And then you're going to go and sort by population. And then you're going to ask the user how many of the most populous do you want to see. They're going to type an answer, and you're going to use a loop to show them that many countries. That's how the program works. So I hope that helps. And of course, as always, you've got really good people to help you out on Piazza, so give them a chance to help you if you struggle with this. But you've done all of the techniques that are required to do this project. It looks scary because the CSV file is large. But this is one of the beautiful things about programming. It doesn't matter how much data there is. If you have it solved for 1 line of data, then you have it solved for 1,000,000 lines of data. So it doesn't actually matter how many lines there are. It'll just scale because the magic of loops, right? So that's the second individual project. And that is, in my notes, part 2. So that's part 2. So now the shifting gears is a lot more drastic. Because to give you more space to complete the lab, we're proceeding with other content. So now we need to do new content. So we'll take a breath and then we will plunge into new content. Okay, so that's a good question. What happens if you see an empty string in the data? Hopefully there isn't any. I think I tried to clean that up so that there wouldn't be. No, there's one here. So Bosnia and Herzegovina have an empty field in there. So what I would do is make those zeros. So if you have a field that comes across as empty and it causes a problem, like put a little if statement in there. If this string has no contents, then make the field value be 0 is what I would do. Oh yeah, there's another. So there are a few in here. This data, by the way, is real. So I didn't make these up. I pulled them from a machine learning website that provides all these data sets. I whittled down the number of fields that we have, but the data set that they give us does have some empty fields. So for empty fields, make them 0. I think we can try this as an experiment. And in fact, let's try it as an experiment. What happens if I try to convert an empty string to an integer? Let's try that out. So this is a very good question. What if I'm getting an empty string from my data input? So I'm just going to go try it out. Where is STOI is in string. Okay, so let me include string. This is how I go about this, by the way, if I want to know. So this is an excellent question. What if the field is empty? That could be a problem, and it's very, very smart to note and to think about it. So let's try. Let's just call it field. If you declare a string like this, you get an empty string. So what I want to know is if I try to string to integer that field, will it run? What happens? Let's see. So there's the converted one, and let's see what happens if it crashes or if it does. It crashes. So here's how I would do it. So excellent question. So we did an experiment, and empty string causes a problem. So what I'm going to do is I'm going to create the integer to store the converted string and initialize it to 0. And only if the field has characters in it do I do a conversion. So if it doesn't have any characters in it, then it stays 0. So outstanding question. So that's how I would do it. Now this does mean that your parsing code is going to have a whole bunch of, your parsing code is going to need a whole bunch of ifs in it to deal with that problem. So outstanding question. And now we know the answer, so wait, that's really good contribution. Okay, so any others about individual project 2 before we do the switching of the gears? Okay, so we're switching gears. We are in week 10, amazingly enough, well past the halfway point. So we're talking about linked lists. Let's just march through the module. So we're doing singly linked lists. And I'm going to draw some pictures with pencil and paper here in a second. And we're going to create a singly linked list with some minimal functionality, and then we're going to build on it over time. We're also going to continue practicing exception handling. So there is a Zybooks chapter on linked lists. My style may be slightly different from theirs, but the underlying concepts are all the same. Your goal is to make the thing work. There are supplemental videos, and they are spoiler heavy. So just remember that the supplemental videos are ones that I shot when we sort of went into emergency mode last spring, and there's a lot of spoilers in them. So the help is there if you need it in the supplemental videos, but if you don't like the spoilers, don't view them until you need it as a last resort, because there are spoilers in there. The first video is probably, but I can't remember. I just know that these 2 videos I shot the week that we started talking about linked list in the last spring. So I thought, why waste the content? I'll share it with you. So some of this is going to be very similar to what I say here tonight. And there might be some slightly different ways that I talk about it. Here's the lab. We're going to come back to that. I'm just going to run through here and check to see what else we have. Okay, so the Piazza discussion. Not everybody pictures in their head linked lists the same way, and not everybody likes drawing pictures. Not everybody likes looking at pictures. Some people like the words. Anyway, if you go searching on the internet for linked lists, you're going to find lots of different presentations. There's visualizations like animated graphic things. There's YouTube videos with like I think there's a school somewhere in Eastern Europe that does like they do dances to show algorithms and stuff. So the point there is to just go find a resource, hopefully one that speaks to you, that explains what is a linked list and how does it work. It could be a video, it could be a website, it could be a an animated GIF, something that you thought, hey, that's an interesting way to explain how linked lists work. And then the reminders page is the normal content, and then individual project 2, which we just talked about. Okay, so I'm going to draw some pictures for a second. So let me change my view. I need the document camera. Okay. And I've tried the graphical pads. I just don't like them. I don't get any flow with them. So I'm just way more comfortable this way. Okay, so what we're adding to our toolkit this week and then building it up over time is called a linked list. A linked list is a data structure. So what we've encountered for data structures, hopefully you have at this point in your career. You've encountered an array, I hope. You've encountered a vector now. And now we're adding a linked list. Technically, right now we are doing a singly linked list, and we'll do a doubly linked list later. So the reason why I wrote all three here is to point out to you that a linked list is simply a place to store a whole bunch of the same kind of something, right? So you can make an array to hold a whole bunch of integers, or a whole bunch of strings, or a whole bunch of country structs. You can make an array to hold a whole bunch of integers, or a whole bunch of strings, or a whole bunch of country structs, or whatever you want. Same thing for linked list. It is a structure that allows you to hold a whole bunch of integers, or a whole bunch of strings, or a whole bunch of country structs, or a whole bunch of whatever it is that you want to store a whole bunch of. So before we look at what linked lists precisely are, I just want to point out to you how these things, so what is common to all of them is that they are collections. They're a way to store a whole bunch of something in one place. And then what makes them different. So arrays, they're all collections, but arrays are fixed size. Which is a limitation of an array. Once you create an array, it is the size that it is. It can't be changed. So that's important because if you're going to use an array, then you need to know in advance how much space you're going to need to hold how many things. And the other thing about arrays is that they are they allow random access by index. So this is one of the great things about an array, is that it is very easy to get to a specific piece of data in them if you know its index. This is the great power of the array, is that they allow random access and it's super fast. It's a limitation of an array that they are of fixed size, but that's one of the reasons why they can be super fast. So that's the cool thing about an array. A vector, they are dynamically sized. So a vector, at least in C++, can grow and shrink as you add and remove things to it. So that makes vectors more flexible than arrays. It also makes them less performant, meaning they require more computer resources to execute than an array does. So an array is very efficient and it's very fast. A vector is less efficient, but a lot more flexible because they can grow and shrink. They also allow random access. By index. And the reason why we have different data structures is because we have different problems, and different data structures sometimes help you solve different problems better or worse. So if I know, for example, that I have a program and it's going to store 10 of something and exactly 10 of something and never more and never less than 10 of something, and I want that program to be as fast and efficient as possible, I'm going to use an array. Absolutely, I'm going to use an array because I will get the best performance and the most efficiency out of the computer if I make that choice for that program. But let's say I have a program where I don't know exactly how much data is going to come in, and I'm willing to make the trade that I get a little bit more flexibility on the size of the thing while I maintain the convenience of random access. So the vector would be a better choice for that program if I don't know precisely how much data I'm going to have to store. But I still kind of want the random access feature, then a vector would be a better choice. Okay, so linked list. They're dynamically sized. They actually are more efficient in terms of getting the extra space that they need than a vector is. You can't see it working in a vector, but a vector, whenever you add something to a vector, it actually has to do work in the background to sort of create extra space. It's not the most efficient sizing mechanism. Linked list, on the other hand, their dynamic sizing is highly efficient. They only create precisely as much space as they need exactly at that moment. They do not have random access. Oops. So this seems like this would then be stupid to use a linked list, but it turns out that there are lots of applications where we don't care about random access. But we do care about accessing things that are first and last in the collection. And you'll see how this works when you implement it. But linked lists are particularly good if you frequently find yourself accessing the most recently added item. Then linked lists are super efficient at that. They're also pretty good at accessing the very first thing that you added to the collection or the very last thing that you added to the collection. They're very efficient at that. And they are more efficient in their dynamic sizing than vectors are. So linked lists waste less computer resources for their dynamic sizing than vectors do. I know you can't see that because we didn't implement our own vector, but that's the case for vector versus linked list. They don't have random access, so linked lists are bad if you are frequently accessing random pieces of data in the collection. But it turns out there's lots of applications where we don't care about doing that so much as absorbing lots of data and finding ourselves most frequently only accessing first and last elements. I'm going to give you an example of that. So here's an example of a use of a linked list. So let's say that you are writing a simulation of a restaurant, and let's say a fast food restaurant like Burger King. So if we're at Burger King, hopefully I get a check from these people for the props. If we're at Burger King, they have a queuing system. Q-U-E-U-E. I botched that spelling. Queuing. Q-U-E-U-E. A Q with ing on the end of it. Lining up. Standing in line. So at Burger King, they have a queuing system, like many fast food restaurants do, or used to, where people enter they come in at the back of the line, and then they exit at the front of the line. So if you were writing a computer simulation of a Burger King restaurant with customers arriving and then being served, This is a very good application for a linked list because you're adding lots of customers as they arrive, but you're only ever accessing the first customer in the list. So at Burger King, you don't know how many customers are going to arrive, so you want dynamic sizing because you never know how long the line's going to be. Every customer comes in at the back of the line, so linked lists are very fast at that, and every customer exits at the front of the line, and linked lists are also very fast at that. So this would be an example of an application, a simulation like this, where we would use a linked list because it is so fast. So that's one example. Another example would be if you've seen an old style jukebox. So an old style jukebox places the records on a stack and plays them. So if I were writing a software system to control a jukebox system, if you think about it, the platters, the records, are placed always at the top. They're played always at the top, and then they're removed always at the top. So a linked list is really good for that, especially if you don't know how many different songs your customer is going to want to play on the jukebox. Then you have all the advantages of the dynamic sizing, and then you get the better performance of a linked list where you're only interested ever in the record that's currently on the top. When it's played, the jukebox would lift that record off and then play the next one on top, and then lift that one off and play the next. So it's only ever adding to the top and removing from the top. And those are just examples of where we might choose a linked list to get maximum performance. Yeah, so same idea for a playlist. Now, if you have a playlist that you want to allow the user to scramble, there's a good chance that you're going to pre-sort sort of randomly, and then use a linked list to play what looks like a random selection of songs. But you could also use an array for a playlist that's randomizing itself. Okay, so those are just a couple of examples of applications of linked list. Now I'm going to draw one. How am I doing on time? Okay, I'm doing pretty good on time. I'm pretty sure if you look at the supplemental videos, you're going to see something similar. So let me show you what a linked list looks like. And then I'll show you what that looks like in software. So that's all a linked list is. It's just a marker in software that's keeping track of what we call the head of the list, which would be the first item in the list. And then what we do is we create nodes in the linked list, and by chaining nodes together, we get a linked list. So a linked list is in software a marker to a node, and then a series of nodes that have been chained together, connected together to each other. That's what a linked list looks like. So in our customers example, so when the Burger King first opens, there's no customers, there's no nodes in the linked list. So as customers begin to arrive, we add them, customer 1, to the list. As they arrive, we add more. The second customer arrives, the third customer arrives, and so on as they keep arriving. Now every time a customer is served, which I ran off the bottom, but I can draw it here. Every time the customer is served and leaves, then everybody else moves forward one. So when customer 1 is served, customer 1 is removed from the list, and then customer 2 moves forward to be the head of the queue, the list. And then customer 3 follows them, and then maybe in the meantime a customer 4 arrived, and so on. So conceptually, this is how I would draw them. This is how they work. A linked list keeps track of who's first in line, and then it actually uses the elements of the list, the nodes, to build a chain of them. We're going to make the node first, and then we'll see how to put it inside of a linked list in software, and then I'll bring in the lab code. So that's a rough picture. These arrows, by the way we do that is pointers. So we use pointers to chain nodes together to each other. I was gonna say something else, but it left my head. So these are all pointers, which means that an empty list, a list that has no contents, is going to be referring to null. A non-empty list is going to refer to a node, and then the last node in a list is going to, instead of being chained to a node, it's going to be null. So we'll know that a list is empty when this marker, this head pointer, is null, and we'll know we're on the last node in a linked list when its link is null. So if I had 2 nodes, so the head would point to the first one's link would point to the second one, and then the second one's link would point to null because it's at the back. So that's part of how these translate into code. The last thing is new and delete. So how do we create these nodes when we want a new one? We use the new keyword. How do we get rid of a node when we don't want it anymore? We use the delete keyword on it. So the things that we talked about last week with pointers, that's why we did that, because linked lists are built using pointers. We create the nodes dynamically, and then we free them when we're done with them, and then we use pointers to build these chains. So let's do a quick example so you can see me build it from the ground up in software, and then I will bring in the actual lab code. And to do that, you're going to want to see it probably. Okay, I'm going to move this stuff to the side. Okay, so let's talk about the node part first. I usually use a struct for this, and I didn't talk about the magic part. So I'm going to do that now. So I usually use a struct for the node. You'll see how I employ it in actual code. But most of the magic of a node is that it itself has a pointer to not itself, but another node. I usually call it the next node. So this is not the node pointing to itself. This is the node having a link that points to another one, the next one over in the list. So that's what that looks like. Now the other thing that I didn't draw in the picture, but I'm going to put it in code now, the whole reason why you have nodes is so that you can put contents in them. So the contents can be anything that you want. It can be a string, it can be an integer, they can be bools, they can be chars, they could be instances of other structs. So the node's job, in part, is to be a link in a chain. Its other job, though, is to carry the one piece of the contents. So now I have to go back and draw a picture again, or I will be not satisfied. So do with the node again. Here's a node. There is next. And then inside of it, conceptually, we are storing the actual contents of that node, which is the data that we're interested in. So in the Burger King example, the contents would be customer information about that one customer, what they're going to order when they arrive, that kind of thing. In the jukebox example, the contents would be a record. And I can't remember what we're doing in the lab, probably integers to make it simple. So that's why the node exists in the first place, is to hold contents, but it also performs the double duty of being a link in a chain of nodes. Turn off. Okay. So let's just do integer. Get rid of this country struct. So there's a node. Now notice right now there's nothing that looks like a linked list, because I just want to show you how do you create nodes. So we would say node, I'll call it N1, and I will make it dynamically. So when you're creating a linked list, its whole job is to be dynamically sized. And the way that you do that is that you only make a new node, a dynamic node, as you have new contents to store in it. So I've made my new node, my dynamically created node. I'm going to put some contents in it. Remember N1, oh, typo. That has to be a pointer, or you can't do it dynamically. So I'm going to make a dynamic node. Now N1 points to the newly allocated node, and then I will dereference it and make its contents be 42, and then I will make its next null. So now I have a node. I guess I'm going to do this. I hope this doesn't start making people seasick. Okay, so I just made this. Now, let's make another one. So I'm going to make another one. I'm going to give it some contents, N2, 99, and N2 next equals null pointer. So now I have two nodes, and I'll go fix the picture so that I have the other node in it. Get rid of this one, and I'll put... So what I have is two completely separate nodes. I have N2 and N1. And just because I want you to sort of at the lowest, most simple level understand how they're chained together. So right now in my code I just have this dynamic node with contents 42, next is null. I have this node, N2, dynamic. Its contents are 99, next is null. Now I'm going to write the code that takes N1's next and points it at N2. So N1 next, point at N2. So N1 next, and when it's a pointer, it's simply the assignment. So if I know that next is a pointer, then using the assignment means I'm really just pointing it somewhere else. So I'm going to point it at N2. And now I have the beginnings of a linked list. So if I go back to my little drawing, I just did this code. So now I have the beginnings of a linked list. So now let's make the linked list part and truly convert this into what can be used as a linked list. Okay, so I usually use structs for the nodes so that I have sort of public access to these two pieces of data. And then often for the linked list part, I'll use a class. Well, but let's, yeah, I'm going to make it a struct for now. Oh, sorry, thank you. I forgot to turn the drawing off. Okay, so I've now made a linked list struct, although in our real application we'll use a class. Yeah, thank you for noticing. I totally forgot to switch that back. So now I have a node. I have a linked list. And a linked list, its main job is to just keep track of who's supposed to be first. So down here, I'm going to make a linked list. I made this static just because you can. Not always, but well, do I want to do that? No, I won't. It doesn't matter. In this case, it doesn't matter. The nodes need to be dynamic, but the list doesn't care. So dot head equals n1. So I'm going to take the linked lists head. Now I'm using the dot notation because the list instance is static. The nodes are dynamic, which is the important part to be dynamic. So I'm going to point linked lists head at n1. All right, so let's not forget because I'm going to go back and put the drawing up. So now I have this head pointer, which points at n1 head. And now I have what functions as a linked list. So I wanted to give you the sense, though, that to a certain extent, the nodes aren't really aware of the fact that they're part of the linked list. They just know I'm a node and I'm connected to some other node. The linked list object is the one who's sort of keeping track of, okay, who comes first? And then we'll have it do some other things as well. Okay, so that's just a crude example, and now we'll go look at the lab and I'll get you some starters. But again, the supplemental videos have massive spoilery stuff in them. So let me get a new one here for lab 10. And then let me go grab the lab, put the code in here. Okay, lab 10. So what do we got? So we got 3. Oh yeah, dang it! I knew I was about to do that too. Okay, thank you. Sorry. So I've created a new lab 10 REPL for myself. And now I am in the lab repo. I'm only going to worry about the linked list parts. The .cpp part that goes with main is the test. So let's go grab the headers. And I will put those in my REPL. So this is slist, singly linked list.h. When we say singly linked list, we mean each node has one link. So there's another kind of linked list where each node has links going in both directions, which we'll do in a couple weeks. Okay, so here is slist.h, and then I will go grab, where did the code go? slist.cpp, which doesn't do anything other than remind me that I need an include. Okay, so now we're set up. Hopefully you are seeing things. You are. Okay. I don't need you anymore. Let's go look at the .h file. So I'll get you a couple of starters here. The supplemental videos have full walkthroughs for this stuff, but I'll pick off a few. Okay, so the thing to do here is to study this code a little bit and see how it's set up. Now you can see something a little bit funny in the way the struct has been done. Now I'm going to put it back, but I just want to show you that all I've done is I've embedded the struct definition inside the class, and then I have star head. So the alternative to this would have been this. Take that out, including that. So I could have done this. Just put the struct up here separately at the top. Everybody's shifted over one too many. So I could have put the struct up here at the top. Here's that next pointer. The contents we call value. It's just an integer. So this node's job is to contain an integer and link to another node. I've also created a constructor in here which should make it fairly convenient to make new nodes that are automatically nulled and automatically contain the value of interest. So I could put the struct here, and then down here at the bottom I could say node star head. Or I can eliminate this separate declaration and undo, 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 undo. Some point I'm going to undo. Okay, so all I've done is sort of embed the struct, but it's the same meaning. So you kind of have to maybe highlight this up to recognize what a node is, and that star head means that head is a pointer to one of these things. I also just want you to see this style because you're going to see it from time to time. So a node has a pointer to another node. We're familiar with that. And its contents we're calling value here, but it's just an integer. And then we have a constructor that should make it simple to create new instances. So the linked list has the pointer to a head. It's also keeping track here of a size, which is, it's keeping count of the number of nodes that are on the chain. So let's go grab all these functions and start to build some of them. How am I doing on time? I always run long. Thanks for your patience if you're sticking it out. So I think everybody tabbed over, which is irritating. Yeah. Okay, so maybe I should leave those comments in there so I can refer to them. So let's do the quick cleanup. I hope so. So I appreciate that, little peeper. I hope that I'm making it worth your while to stick it out. I want you to see sort of from the ground up where these things are coming from, because when you get into the lab now, all of a sudden all the code's there. So the trick about a list is it's not nodes. A list is like a node manager. So a list is keeping count of how many nodes are out there, and it's keeping track of which is the first one. But otherwise, a list is not really intelligent about what the nodes themselves are up to, who's linked to who, and who's got what contents in them. The linked list is not super intelligent about those things. Okay, so we'll do this part, scope resolution, so that this all works. All right, now we're ready to do some implementation. I should have, yeah, let me get the notes or the comments for the constructor so that we have those to refer to. Okay, so the constructor part. So when a list is created, It needs to do something with that marker that it keeps track of who's the first node, and it needs to make sure that its counter is set to 0. So those are pretty easy. That's it. So that's the state of the linked list when it fires up. It's tracking 0 nodes. And because there's 0 nodes, there is no first node at the head of the list to keep a marker on. So that's it. That's how you construct a linked list. Okay, so that one's fairly straightforward, and also the comments told you to do that. So now let's do some of the harder ones. Think CRUD, because whenever you're writing a class with functions around a data structure, in this case a linked list, you're usually going to want some part or all of the available sort of CRUD function options. So push front is a create CRUD function. We're going to take a value and add it to the list. So push front means that, now I got to draw a picture real quick. When we say push front, when we're pushing front, what's happening is every new node is coming in front of the former head. So when we're doing push front, this is like the worst Burger King in the world. So push front means that the newly arriving customer gets to go right to the front of the line. That's what push front does. Which would be terrible if we were doing a Burger King simulation, but there are systems like actually the jukebox where we want the newest thing to go sort of at the top or the front or at the head. So when we push front, if we were to push front on this list, so push front, let's say 30. Notice, by the way, that that's just a value. So to push front 30, we have to create a node to hold 30. And then we link the node up so that it is now at the front. So the head pointer has to move from 20 to 30 to push front. Okay. Dock camera off. Okay, so to push front, what does that look like in code? The first thing is we need a node to put this value in. So I need a node star, I can just call it n, it doesn't really matter, equals a new node. And I can go through the manual process of n next equals null pointer and value, that was what it's called in the struct, equals the value from the parameter. But I don't have to do all this extra work because the node struct, if I go look at it, it has a constructor in it already. So I can make a new node with a value and it does the nulling and the assigning of the value for me. So I'm going to do that instead of all this mess. I'm just going to use the constructor. So if I use this constructor, then the link is nulled and the value is loaded into the node. So here's my new node. Now the trick is I got to link it up. So back to the drawing board. So the trick is let's say that I have 10 and I'm about to push 20. So the trick is I make the new node for 20 and I point it at the same place where head is currently pointing. This is going to be null here. So to put the 20 at the front, the first step is to take this new node's next and point it at the same place where head points. Turn that off. So I'm going to take its next and point it at the same place where the head is currently pointing. So this next pointer is the same location, it's the same node that the head pointer is currently pointing at. The second step is to move head over so that it's now pointing at the new one. So head needs to point somewhere new, and it's at the new node. Turn that off. If I say it, I think I'm less. So I need to take head now and point it at that new one I just created. So I create a node. I link it to the node that's currently at the front, and then I move that marker to the newly created node. And then the last step is I just added a new node, so I need to increase the size by 1. That's push front. Okay. Probably spoiler alert, I'm probably going to walk through, in the time that we have, get size, that's just the size variable. Empty, the easiest way to do that is see if the size is 0, that's empty. So those two should be okay. Let's do front, and then we'll do to string together. Okay, so the front. The idea here is not to return the node that's at the front, but to pluck the data out of it. Not remove the data, but really just let someone see what the data is inside of the node at the front. So in my picture, front right now should return 20. That's the data inside of here. Now, we have to be careful because if they ask for the front piece of data when there's no nodes there, this can crash. So we need to address that problem, that if you ask for the front piece of data and there's no node there, we need to prevent the crash. Close that. And that's what this throw is about. So you remember we've done some throws around null pointers. It's the same thing. So if the head is pointing at nothing, double equals, right? We want to know if head's value is null, then we're going to throw a logic error saying empty list. Otherwise, we can do as requested. So this if check guarantees that if they try to get the front piece of data from a non-existent node, that they get a signal back from us that there's no nodes there, the list is empty. Otherwise, what we're going to return is not the head node itself, but the value inside of it. One thing that's weird about these data structures, by the way, there's rarely a function that takes very much code. It's super complicated code, but there's rarely very much of it. I highly recommend that you draw pictures. Drawing these pictures like I've been drawing takes practice, but it is a very powerful way to develop an understanding of how these structures work. So it takes a lot of practice to draw the pictures, but eventually you can start to draw pictures and you can use them to debug your code. So the sooner you start drawing pictures and trying to match what you see in the picture to what you see in the code and you get comfortable with that, the sooner you will master these complex structures. The code itself never looks like very much. So that's front. Here's that little thing saying I might throw an exception, which we did. Okay, so now the hard one. Let me see what we have for includes up here. String. Okay. So now to string, and the tricky bit is the last one shouldn't have a comma, so you're going to see how to do that. So I'm going to make an O-string stream out. Ultimately, I'm going to return that as a string, and then in between is the good stuff. Okay, so here's the trick. I need to iterate over a linked list and look at the data in every node without breaking the list. So let me go last one. Thanks for your patience. This is it. Okay, so if I'm doing this to string, what I would want is 30, 20, 10. That's what I would want to come out of here. Now I have to figure out how do I walk from the front of the list to the end of the list without breaking it. So I will tell you that you need to be very careful of this head pointer. So the trick is to create a temporary one. Start it in the same location as head, but then take this temporary one and march it down the list until it falls off. So temp, 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 null, we're done. So I'm going to create a temporary pointer to this same one that head points to. And this is going to be a little bit of the back and forth to the pictures again. In code, though, we're going to say node star temp equals head. So notice I did not create a new node. I don't want a new node. I want the old nodes. I just need a pointer that points to the same place as head does. So that's what I just drew in the picture. Now I'm going to say while that one is not equal to null. So this loop is how I'm going to detect when I've walked that temp across and it fell off the end. So while it's not null, I'm going to attach the value that it's pointing to, followed by a comma. Now that's not perfect, and we're going to need to fix it. And then once I've gotten the data out of temp, then I'm going to move it to the next one over. Pretty crazy. So let's sort of do a hand trace of that in the drawing. So node star temp equals head. So I'm going to get, while temp is not null, there's a node there, I'm going to get the value, tack a comma on, and then I'm going to say temp equals temp's own next. Temp next. Get out of the way, push front. So now temp is moved over. The while loop checks it to see if it's null. It's not. So we grab the value and a comma. And then we say temp equals temp next. So we slide it over. We check it for null, the while loop does. It's not null, so we get the 10 and a comma. Then we slide it over. Temp equals temp next. And then the while loop's going to say is temp not null. Oops, temp is now null. We're done. So there's one catch here, is that there's an extra comma on the end, and the spec says no comma after the last one. So this is, yep, so we're down to, this is it. I'll ask one question and then we'll solve this one and we should be good to go. So there's something special about the very last one that we can use to detect when it's the very last one, because the very last one should not get a comma. Only the nodes that aren't the last one get a comma. So the node that's the last one should not get a comma. So what is special about this last node here that makes it different from the other two? because we can use that, what's special about it, to improve our algorithm. Something's different about the value or the link. It points to null instead of another node. Outstanding. So the last one's next is null. So we can use that information. Outstanding. Good answers. So right here, we're going to take the comma off, and we're going to only add the comma in a special case. So if temp next is not null, that means we're on a node that has more neighbors next to it, which means that we're on a node that can get a comma. So once we reach the last one, its next will be null and it won't get a comma. So notice how sort of unsatisfyingly little amount of code that is, but it is highly complicated code. This is sort of next level stuff. It's got pointers all over the place. It's got a complex looping algorithm. It's got a little sort of one-off test in the middle. This is not easy code. So we should all be humble about it. It's very easy to make mistakes, and we learn by them, and we fix them, and then we move on to the next one. But this is a lot harder than when you're sitting there by yourself than it looks. So make sure you leave yourself time. Don't feel bad about yourself if you have problems with pointers, because if you are still working in C++ 20 years from now, you will still make mistakes with pointers, I promise. Watch. You're going to watch me make mistakes with pointers before the semester is over. So it's not a thing to be worried about, it's a thing to fix. So remember, you have Piazza, you have the Canvas inbox when needed, but Piazza is way better because then everybody can benefit by it. So that's it for me. I hope that is useful and helpful. I know I kind of ruined the fun of some of the labs, but since we're not together and I can't really see your faces and see what you do and don't grok very well, I feel like it's safer to just sort of walk through it together and explain exactly what it is that we're doing. So if you have courage, you might start with a blank screen and see if you can rebuild these things, thinking through the problems. But now you have the video. I did leave these two unimplemented. But otherwise, I think we're done. So thank you, and thank you. Thank you. Great questions. Great questions and great answers, as always. So I appreciate your group for being engaged, and you're still going strong. So thank you. I appreciate it. You guys have a good night, too. Have a great week. I will see you on Tuesday next week. You have the project, so I know that adds stress. You have all the skills that you need, and you have Piazza to fall back on if you get stuck on a thing, and you have really good classmates for stepping in to help out, so don't forget that. So good luck on that. I hope it goes well. That's my dream, is for everyone to get perfect, and it just be a fantastic learning experience for everybody, and hopefully that's the way that it is. Anyway, have a good night, have a good week, and I'll see you next Tuesday.